Okay, we've got this new design of kettle where there's a vacuum space here in between the inner and outer plastic layers. Here's the water. You boil the water, leave it standing, and the first question is, how does this design reduce the heat loss? How does it keep that water warmer for longer? Well, this is a vacuum, and a vacuum is empty space. So there's literally nothing in that space, no air molecules, nothing. Which means that heat loss by conduction is actually impossible through that space. It won't be a perfect vacuum, but assuming it is a perfect vacuum, then conduction is impossible. Here's all the hot water, and conduction through there cannot happen because it's a vacuum. Conduction can only happen through a medium, and if there's no medium, if there's nothing there, it can't happen. Because conduction is when all the hot molecules are vibrating and they bounce into the ones next to them and they bounce into the ones next to them and pass the heat energy along. But if there are no molecules in here, then that can't happen. Okay, so this is worth 2 marks, this question. That's the main reason. However, to get 2 marks, you should also mention it will reduce heat loss by convection as well. So conduction is the main way, but also mention convection. So yeah, that's the main one. Convection is when a whole chunk of a fluid, that is a liquid or a gas, moves and carries the energy with it. For example, warm air above a radiator in a room. The warm air rises. And again, because this is a vacuum here, if there are no molecules in it, then convection can't happen because there's nothing to move and carry the energy. Okay. This design doesn't reduce loss by radiation. Often in exams you get a question where they've got some kettle or something and it's got a silver lining and you have to explain why the silver lining reduces heat loss. That is radiation. The silver lining reflects heat radiation from the hot water back into the inside. But they haven't mentioned a silver lining in this case, so don't mention radiation. Although often I'm just saying, often that comes up in an exam. Okay, anyway, right. So next bit, they tell us that the heat loss from this water to the surroundings in 2 hours, yes, is that. They tell us that the mass of that water is that. They tell us the specific heat capacity of the water is that. The initial temperature of the water is 100 degrees C, it's just boiled. And we have to work out the temperature after 2 hours. Okay, so the relevant equation here is that energy is mass of the water times specific heat capacity of the water times the temperature change of the water. So the energy loss from the water is the mass of the water times the specific heat capacity of the water times the change in temperature of the water. Sometimes that's written delta theta, like that, or sometimes delta T. The delta means difference or change in. Okay, so we have to work out the temperature, so we need to rearrange this equation to get temperature by itself. So divide both sides by MC, boom, 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 and we get change in temperature is change in energy over mc. Stick the numbers in. So theta is, in 2 hours, the change in energy is 46,200 joules. When you're putting it in the equation, you have to get it in the right unit. Joules is the correct unit, over mass, 0.5. That should be in kilograms, and it already is, so we don't have to do anything. Times specific heat capacity, that's already in the correct units. So it's 4,200. So, therefore, the change in temperature is, stick that in your calculator, and it comes out to be 22 degrees. Now, it's asking us for the temperature after 2 hours. So don't forget, if the initial temperature was 100 degrees C, after 2 hours it's fallen by that, 22 degrees C. So the final answer is 78 degrees C. Okay, right. Now we have to work out the power output that represents to the surroundings. So it's lost that much energy, okay, in a time of 2 hours, right? Now the power output from the water to the surroundings, power is rate of change of energy, or rate of delivery of energy. It's not rate of change of energy, it's rate of delivery of energy is a better way of putting it, or rate of energy transfer. It's energy rate anyway, which basically means power is energy per unit time. That's what rate means, per unit time. Energy divided by time. Okay? So, the energy is that, which should be in joules, it already is, so that's fine. 46,200 divided by time. The time has to be in seconds. So we have to convert 2 hours to seconds. And you do that like this. 2 hours, there's 60 minutes in an hour, so 2 hours times 60, that's how many minutes, and there's 60 seconds in a minute. So in 2 hours, there is 2 times 60 times 60 seconds. Stick all that in the calculator, and you get 6.416 recurring. 6.416 recurring. Don't leave it like that. It doesn't tell you how many decimal places it wants it to. So you have to choose yourself and choose something sensible. 1 decimal place is sensible. So that one leaves the 4 alone. So it becomes 6.4, and units of power is watts. 1 watt is 1 joule per second. I think that's it. Yeah? I hope that's all right. Not too bad, I think. Yeah.